All right, so I guess we'll get started. In the lectures last week, we had a pretty detailed look at the scattering cross-section. Just to give you a reminder, where we considered how would an incident beam of objects of some sort be deflected or scattered by some potential, whether it would be attractive or repulsive. And we derived an explicit analytical expression for this differential scattering cross-section, and also saw how it would be related to the total scattering cross-section, which in fact could diverge. Now, we ended by starting up on a new topic. Namely, the kinematics of rigid bodies. And I think we defined the key elements in this topic, what kinematics means and what a rigid body would mean. So if we are to deal with this topic, one of the first things which might be useful for us to consider is what kind of coordinates are beneficial to use to describe this type of system. Because we know that in Lagrangian formalism, we need a set of independent coordinates, the so-called generalized coordinates. So which set of coordinates would be useful for us here? If we consider a rigid body which is composed of large m particles, in principle we would have 3n degrees of freedom. However, the fact that the body is rigid introduces some constraints which reduces the degrees of freedom. Namely, the fact that for a rigid body, the distance between any 2 points or particles, I and j, has to be a constant. So the number of degrees of freedom is reduced. So how many degrees of freedom do we have? Well, let me suggest to you that we need 6, that we have 6 degrees of freedom for a rigid body with n particles. And so let me justify this statement. It is sufficient to determine the distance to 3 points in order to specify the location of any other given point in space. So if you want to characterize some point in space, it's sufficient to characterize the distance from this point to 3 other points in order to uniquely determine its location. So in other words, if we know the position of 3 points in a rigid body, then by these constraints, we know the position of all of the other points in the body, and hence we know the shape of the body. So to see this, we first have to specify the location of point 1. How many degrees of, or how many coordinates do we need to specify the location of the first point? In general? 3. Okay. Now we need to specify 2 more points. So let's consider the second point. And now we only need 2 coordinates. And the reason for why we only need 2 points, 2 coordinates to specify in point 2, is that point 2 has to be located on the surface of a sphere with point 1 in the middle and with a radius C12, which is a constant. So know that due to the fact that it's a rigid body, the distance between point 1 and point 2 is a constant. And so if point 1 is specified, well then point 2 has to be somewhere along a sphere. So we need only 2 coordinates to specify its position on a surface. Okay. Well, as you might guess, for the third point and the last point we need to specify the points of all on the entire rigid body, we only need 1 coordinate. Because this point has to be located at the intersection between these 2 radii, which becomes a circle. And so point 4 will be completely fixed. We will know the position of point 4 just from the constraints once we have identified the first 3 points. So there are, as stated, 6 degrees of freedom to determine for the rigid body, for any rigid body. And that's better than 3n, which can be quite large. So moving on to the question of how or what types of coordinates are good to use to describe such a system. Well, imagine we have two different coordinate systems, one stationary, fixed here, and then we have an additional primed coordinate system here, which you may think of, for instance, as being attached to the rigid body, which may or may not be rotating. So these ijk and ijk prime vectors here and here denote the unit vectors in each of the systems. Now, if we want to specify the position of the rigid body, which has this coordinate system attached to it, we know that we need 6 degrees of freedom. We need 6 coordinates. Well, 3 of them should go to specifying the origo of this coordinate system. So you can think of this coordinate system, for instance, as being attached to the center of mass of the rigid body. So we need 3 coordinates to specify where is the rigid body in space. That's 3. So the last 3 goes to specifying the orientation of this rigid body relative its center of mass. So 3 coordinates to specify the origo or center of mass, and then 3 coordinates to determine its direction. Now, to accomplish this, we need to find some way to express vectors in this coordinate system in terms of vectors or coordinates in this coordinate system. And this is one way of doing it. We're basically taking these unit vectors I, j, and k along the x prime, y prime, and z prime axis. And we're saying that these should be possible to express as a linear combination of the unit vectors in this system. This should be possible. Any vector here we should be able to represent as some linear combination of these unit vectors. Just as you can take any vector in 3D and represent it as a superposition of I, j, and k with different weights. These coefficients here are known as directional cosines. And why is that? Well, You see that alpha 1 is given as the scalar product between I prime and I, which is given as the cosine of the angle between these two vectors. So each of these coefficients that give us our linear system of equations can be expressed as cosine between two vectors. And we have 9 of them. According to our previous arguments here, some of these directional cosines should be quite redundant. They shouldn't be necessary, because we know that it only takes 3 coordinates to determine the direction of something, but we have 9. So somehow all of these cannot be independent of each other. So the question is then, how are these related? Do you have any ideas? Which essentially then should reduce the degrees of freedom from 9 to 3. Yes?
They should all be in a right-hand system with a 90-degree angle between them, so you can express them as cross products probably to each other.
That's true. So you're saying that they belong to a right-hand system, and so they should be orthogonal to each other, 90 degrees. So basically, for instance, I prime dot j prime should be 0. So we get this equation. And then we're basically able to take one of these directional cosines out of the equation, because we can express alpha 1 through the rest of them by moving this over to the right-hand side and then dividing on beta 1. So you see that alpha 1, for instance, is not independent of all of these. It's in fact determined by these through the orthogonality of the unit vectors. So we have 3 orthogonality conditions, but in addition, we have a normalization condition. For instance, that I prime squared should be equal to 1 because it's a unit vector. And similarly for j and k. So we also have 3 normalization conditions. So we have 6 of these conditions in total, 3 orthogonality conditions and 3 normalization conditions. And by then, we've achieved what we wanted, namely to reduce the 9 directional cosines to 3 degrees of freedom. So these directional cosines seem pretty neat. I mean, we can write them up in a pretty compact way like this, relating any vector in the prime system to the original system. So could we use the directional cosines as our generalized coordinates if we wanted to write down the Lagrangian? What do you think? There are two possible answers. I see a thumbs down, okay? How come?
Because they're not independent.
Exactly. The generalized coordinates we want to use for a Lagrangian have to be independent. And these are not independent. We just show that they're in fact related through these 6 orthogonality normalization conditions. However, we can construct 3 independent coordinates from these. And these we should be able to use as generalized coordinates. So we can formulate a set of 3 independent functions of these directional cosines which are suitable for use as generalized coordinates. So that was just to give you an introduction concerning these different coordinate systems, whereof one may be rotated compared to the other, and how many degrees of freedom we need to describe such a system. So when dealing with rotations, it's useful to go through some mathematical details, what is known as orthogonal transformations. So let me just change the notation slightly from x, y, z to x1, x2, and x3. And the reason for this is simply that it's more convenient to use x1, x2, and x3 as the variables, because then we can just use, for instance, xj as a generalized, to describe each of them. It's easy to write summations, for instance, with x1, x2, and x3 instead of x, y, and z. And then we have some rotated system, the prime system here. So our set of transformations becomes like this, where I've now also renamed these directional cosines to A11, A12, etc. And this is to make them fit more easily into matrix notation. And these coefficients, Aij in general, are constant. So they're independent on these coordinates. They're just some constants. So this kind of linear transformation corresponds to a rotational system. So we can write all of this very compactly like as follows, by using the sum convention. Repeated indices on one side implicitly means summation over that index. So here it's implicit that we have summation over j. And so keep in mind that this is linear precisely because Aij, these coefficients are independent on the coordinates. So everything here is linear in x. If these constants were depending on x, well then we wouldn't have a linear set of transformations anymore. Okay, so what can we say about this type of transformation? Well, if we have some vector r in the original coordinate system, and we then rotate the coordinate system to the primed coordinate system here, the length of the vector r should be unchanged. Just its direction should change. So the length squared, or the norm squared of r, is simply xi. So this is x squared plus y squared plus z squared. And it should be equal to xi prime, if the length is conserved. So if we now insert this equation here and thus express the primed coordinates through the original ones via these coefficients a, we get this. So I've just inserted this into here. Now, in order for this equation to be satisfied, we see that these coefficients have to satisfy this. And this is a sum, because we have repeated indices I on this side. And in fact, these are just the 6 conditions that we expressed explicitly over there for the directional cosines. These are in fact 6 equations. J can take any value from 1 to 3, K can take any value from 1 to 3, 6 equations. So these are the normalization conditions and the orthogonality conditions comprised or condensed into one equation. This set of linear transformations is known as orthogonal if the coefficients satisfy this equation. So this is not necessarily an orthogonal transformation, this is a linear transformation. But if the coefficients satisfy this criterion, then it's also an orthogonal transformation. So all of these coefficients that define our transformation when going from the unprimed to the primed coordinate system can be expressed neatly through this transformation matrix, which has matrix elements A, I, J. So let's consider an example. Let's consider a rotation in 2 dimensions. So our rotation matrix looks like this. Our orthogonality conditions can be condensed into this form. And in 2 dimensions, how many orthogonality conditions do we have? We had 6 in 3 dimensions. Okay, how do you reason to arrive at the conclusion 4?
Because they can vary from 1 to 2 both.
Mm-hmm. That's true. So J goes from 1 to 2 and K goes from 1 to 2. So in principle, it looks like we should have 4. And in fact, I now realize that what I said previously was slightly misleading, because I said that in the 3D case, J would vary from 1 to 3 and K from 1 to 3. So, but following the same reasoning in 3D, that should mean we had 9 orthogonality conditions, right? Because if this one goes from 1 to 3 and K goes from 1 to 3, then we have 9 conditions. But we have only 6 in 3D, as we saw. And for the same reason, I see your reasoning. 4 is a perfectly good suggestion, but in fact we have 3. And the reason for this is that we actually have a redundancy here. Let me show you. So we have, for instance, A1, 1. This should be equal to delta 1, 1 plus A21, A21. This should be equal to 1. Okay, so that's one condition. Next, delta 1, 2. So we have A1, 1 like this. And then finally, A12, A12 plus A22, like this. So we have 4 equations. That's entirely correct. But you see, these 2 equations are identical. These are scalars, so the order is not important, they commute. So in fact, we only have 3 normalization orthogonality conditions. And in the same way, you can show that 3 of these are equal in 3D, so you have 6 there. So you have 3 in 2D and 6 in 3D. Well, we have 4 of these coefficients. We have 4 matrix elements, and we have 3 orthogonality conditions, which means that we should have simply 1 degree of freedom. So we have 4 matrix elements, or directional cosines, if you will. And we have 3 orthogonality conditions. So does this make sense? To have only 1 degree of freedom when considering 2D rotation? Well, I think so. Because we see that we only need 1 angle, phi, for instance, to specify the orientation of this prime system relative to the original one. So the rotation angle is the only degree of freedom in 2D. Now, this would be different if we allowed for our linear transformation to change, for instance, the norm of vectors, so the length wasn't preserved. But if we have a system where the length is preserved, so we have normalization and also orthogonality, then there's only 1 independent variable. If we now consider this figure, which demonstrates rotation, we can actually infer how these primed coordinates are related to the unprimed ones via this angle. So just by considering the geometry of this figure, we see that these relations hold. So our rotation matrix expressed through this one function of the directional cosines, which is independent, namely phi, can be expressed as follows. So this is a general rotation matrix in 2D. So let's see now if this actually satisfies the orthogonality conditions. So keep in mind that this is A11, A12, A21, A22. I think we wrote them over here, yeah. So consider these equations over there, the four orthogonality conditions, which in fact are only 3 for a 2D scenario. The first one this one, when inserting what A11 and A21 are, gives this. So that's okay. And then we also have the last one, which is also equal to 1. And then we have the two in the middle, which are in fact the same equation. And it holds as well. So this rotation matrix seems to do the job. Now we see that if we define these two vectors, the transformation equation can be written quite compactly like this. So the vector in the new coordinate system is given as the transformation matrix multiplied with the old one. So that's why it's convenient to express it in matrix form. Now, there are two ways to interpret what this equation actually means. And I'll tell you about this after the break.